Welcome back to the Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing a history of mathematics. We're going to do more ancient Greek topics. This time what we're going to do is greatest common divisors, which will involve to find the greatest common divisor of two positive integers. We're going to use the so-called Euclidean-Bezoutian algorithm. And what this is going to entail is finding the greatest common divisor of two integers and then writing it as a linear combination of those original two integers a and b. Let's get to it. All right, here's the definition of the greatest common divisor of two positive integers. Let a and b be positive integers. I'm always going to assume a is the big one, but it doesn't really matter. The greatest common divisor of a and b, denoted g.c.d. ab, or when I'm trying to talk about it, I just want to call it one integer because it's going to be some positive integer, so I'm going to call it d. What is this? This is the largest positive integer dividing both a and b. So we know that, or we should know that, for each integer, a can be written as 1 times a and b can be written as 1 times b. So this says that 1 divides a and 1 divides b for any two positive integers. So we must have that d is at least 1. Should make sense for the positive integer, or for the greatest common divisor. It should be a common divisor. So that should mean that we divide both of these. And coincidentally, what this means is if and only if a is a multiple of d and b is a multiple of this greatest common divisor d. So we should have these two properties as well. And then why is it the greatest common divisor? Mathematically, this is going to say if there's some other integer c which is the common divisor of a and b, then this number c also divides d. So d is the largest one that divides both a and b. And then what we're going to want is the first half of this to find the g.c.d. This should be the first question you ask yourself. Now that I know what a g.c.d. is, I give you two numbers, 8 and 12. How do you find the g.c.d.? This is going to be a nightmare. So what we're going to do is ask first, how do we find the g.c.d., which will luckily be the Euclidean algorithm. And then we want to find two integers s and t such that we can write the g.c.d. as a linear combination of a and b, or this way, essentially. And that will be the Bezoutian half of the Euclidean-Bezoutian algorithm. Let's do an example, and then we'll do the Euclidean-Bezoutian algorithm. All right, example 1, find the greatest common divisors of 8 and 12 by doing first brute force, listing all the positive divisors of 8 and 12. This isn't going to be fun for large integers. Finding all the positive integers and listing them will be a non-trivial game in general, but we'll do that. And then we'll get the idea of the Euclidean algorithm and why this is going to be much better than listing positive divisors. So what do I mean by list all the positive divisors? If I list all the positive divisors of 8 and I list all the positive divisors of 12, then that's just going to say that I just picked the largest integer in both of the lists, which will be 4 coincidentally. So I have 8. How do I do that? It is 2 times 4. 4 is 2 times 2, so I get the factoring tree. So that says 8 is 2 times 2 times 2, or 8 is 2 cubed. And then 12 is going to be the same thing. I'm going to do 2 and 6 and 2 and 3. And so 12 is going to be 2 times 2 times 3, or 2 squared times 3 to the 1. This is the prime factorization of 8 and 12. And then what do I do with that? I can list all the positive divisors. The best way to do this is make little tables. I try to find the integer just less than the square root of both of the numbers. So how am I going to do that? Let's do it like this. I find the perfect square just less than 8, so that's going to be 4 is less than 8, so that says that 2 is strictly less than the square root of 8, and for 12 I'm going to have 9 is less than 12, so this says that 3 is strictly less than the square root of 12. Why is that useful for me? Then I can get these little boxes. For 8, all I needed was to list all the integers up to the number less than the square root, so 1 and 2, and then I should get the pairs for 4. So the positive divisors of 8 are all the powers of 2 up to 2 cubed, 1, 2, 4, 8. For 12, I list all the integers up to the integer less than square root of 12, which is 3 this time. So I list 1, 2, 3, and coincidentally, this time I'm going to get 1 times 12 is 12, 2 times 6 is 12, and 3 times 4 is 12. 3 times 4 is 12, which you can get from the factoring tree. Try this for larger numbers. This is the idea of which was really easy for 8 and 12, but can be extremely hard for large integers. This is the way to find and list all the positive integers of 8 and 12, or two integers, 1, 2, 3, 4, 6, 12. Then what I do with that is I can pick all the positive divisors in there. 1 is a positive divisor of both of them, always. 2 happens to be a positive divisor. And then 4 is the largest number in both lists. So 4 is the greatest common divisor of these two numbers. This says that the g.c.d of 8 and 12 is equal to 4. And notice, if you have any other common divisor, 1 divides 8 and 1 divides 12, which implies 1 divides 4, and 2 divides 8 and 2 divides 12, which implies 2 divides 4. So it's the largest positive divisor. It's greater than or equal to 1. It divides both 8 and 12. 8 is 2 times 4, and 12 is 3 times 4. So 4 divides both 8 and 12, and it is the largest one. Now let's do the Euclidean algorithm. For the Euclidean algorithm, the idea is we're going to use iterations of the division algorithm using specific people. I'll tell you by rote how we're going to do that. Let's do this for 8 and 12. 12, we start off with the larger one. We divide the smaller one into the larger one and find a quotient or remainder. So we're doing this. 12 is one group of 8. Subtract, and I'm going to get a remainder of 4. So 12 is 1 times 8 plus 4. 8. And then now I'm going to use these two guys. Divide 4 into the 8. And that's going to give me 2 times 4 plus 0. I stop when I get a 0 remainder. And the last non-zero remainder in this process, in this case it only took us 2 steps, it was really quick. I picked small numbers to show. But this says this is the Euclidean algorithm, and this is the way we use iterations of the division algorithm, so we get a 0 remainder. The last non-zero remainder is the g.c.d every time. This is a much better way to systematically find the greatest common divisor in a few finite number of steps. So this says again that the g.c.d of 8 and 12 is equal to 4. And I had to do 2 things quickly. That's a much better process. Now let's do it one more time with bigger numbers, and we'll get the Euclidean-Bezoutian algorithm, how to write it as a linear combination as well. All right, example 2, we'll use relatively small numbers so we can see how this Euclidean-Bezoutian algorithm is going to work. I'm going to do the horrible Bezoutian algorithm to show you sort of and justify why this clever trick works, and then I'm going to give you a clever table, and then we'll do one more example so that you'll have the full idea of how to use the Euclidean algorithm to find the g.c.d, and then the Bezoutian table to find the linear combination of the g.c.d as a linear combination of the original 2 numbers a and b. So what do I want to do? Find the greatest common divisor of 42 and 15, and then write it as the g.c.d of 42 and 15 as s times 42 plus t times 15 for some integers s and t. First of all, we use the Euclidean algorithm. So I divide this. 42 is going to be 2 groups of 15, which is 30 plus 12. Again, if you can't see it, what we're doing every time is long division. So we're going to get 30 minus 12. We stop when the number is less than this guy, the divisor. And so that gives us the first row. Then I do 12 and 15. 15 is equal to 1 group of 12 plus 3. And 12 is 4 groups of 3 plus 0. This says that we can stop because we got a 0 remainder. And the penultimate or last non-zero remainder is going to be the greatest common divisor. This tells us that the greatest common divisor of 42 and 15 is equal to 3. Now what I'm going to do with that specifically is cleverly what Bezout, a French mathematician, hundreds of years later after Euclid comes along and says cleverly he's going to take these remainders and write them a clever way. So what he's going to do here is write 12 as 42 minus 2 times 15. I'm going to move this one to the other side of the equation, and I'm going to move this one to the other side of the equation. So I'm going to write 3 is equal to 15 minus 12. And starting with this one, 3 is 15 plus actually negative 1 times 12. But I know what 12 is. 12 is this guy. So when I put that in there, I can replace this 12. So that tells me I get equals 15 plus negative 1 times what is 12? 12 is 42 plus negative 2 times 15. I'm keeping the coefficients specifically because I'm trying to find these S and T guys. I'll give you a table in a second. Then what that does is that says 3 is equal to, again, I distribute this guy onto both. I'm going to get negative 41, and negative 1 times negative 2 is positive 2, plus a 1 is going to be equal to 3 is equal to 3 times 15 plus negative 1 times 42, or 3 our g.c.d of 42 and 15 is equal to negative 1 times 42 plus 3 times 15. That's exactly what we were looking for, the S and the T. This is how we write the g.c.d as a linear combination. So the second half, clever business, I now have, and I will show you, I have an actual table that will work quite nicely and will give you what you want. So what, instead of doing this horrible business now, let's ignore that, and I'll give you a magic table. Here's what you do every time. I take this, I cross off this last row. I don't need this, I need these guys, and I use the quotients bottom up. So now I have 2 quotients, 1, 2. And so I need a table with 3 rows always, and this time 4 rows. 3 columns, sorry, and 4 rows. Why? The first 2 up here are duds, and then I put 1, 2 here. 1, 2. In this column, I put 0, 1 to start with, and then these are going to be the coefficients on 42 and the coefficient on 15. Here, because we were solving for the remainders each time, there's going to be a negative every time I do it. So we're going to get negative plus to get our coefficients. So it'll be negative times this guy. And then what do? I use color coding if I want. Now, how do I do this? Once I've color coded, I have 1. I take the quotient 1, I multiply it by the number above this 1, and then add it to the number above it. In the first case, you'll just get the number itself again. But now when I do this, I have 2 times 1 plus the blue 1 above it, which will give me 3. And what does that say? That exactly tells me I have a negative 1 in front of the 42, and I have a positive 3 in front of the 15. So this tells me that 3 is equal to negative 1 times 42 plus positive 3 times 15. And again, 45 minus 42 is 3, equals is equals. Now let's do that with it one more time with some slightly larger numbers so that we can see how the Euclidean-Bezoutian algorithm works to find the g.c.d of 2 numbers and then write it as a linear combination of the original 2 numbers. One more time. All right, to finish off, we'll do example 3. Find the greatest common divisor of 581 and 427. And then write that greatest common divisor as a linear combination of 581 and 427. How do I do this? First of all, I have to use the Euclidean algorithm. So 581 is equal to, they're close enough where if I subtract them, I'm going to get borrow 11, there's going to be 4, 5, 1. So I'm going to get one group of 427 plus 154. Same thing, if I want 154 plus 154 is going to be what? 8, 10, 308. If I do 154 again, I'm going to get 12, 6, 4. So it's too much, so I have to use 3 of them. So what that says is 427 minus 308 is going to be borrow 117 is 911. So this tells me now that what? 427 is equal to long division. Essentially, I'm just using, they're fairly close to each other. So this is going to be 2 groups of 154 plus 119. Now I can subtract again. 154 minus 119, or 414, 9 should be 5, and then 435, so we should get 154 is equal to one group of 119 plus 35. Now what we're going to have to do is long divide the 35 Again, you can just get rid of these as you go. We don't need these. This is where I'll draw the table, but now I have 119, and I have to divide it by 35. So 35 plus 35 is 70 times 1 times 2. I'm listing the multiples. 35 is going to give me 105 times 3. Then 35 will give me 140, which will be too much. So this is going to be 3. I'll get 105, which will be 14. So this says that 119 is equal to 3 groups of 35 plus 14. 35 minus 28 is going to be borrow 2. 15 will give me 7. So this says 35 is 2 groups of 14 plus 7. And then 14 is going to be 2 groups of 7 plus 0. What does that tell me? That tells me I can stop. And my GCD is going to be 7. GCD of 581 and 427 is equal to 7. The largest divisor, the largest positive number that divides both 581 and 427 is 7. Now what do I do with that? I get rid of all this junk. And I write my Bezoutian table. What does that do? Or how do I do that? I block off the last row because I don't need this quotient, be careful, and then I need these ones bottom up. I have 1, 2, 3, 4, 5, so I need 7 rows in my table. Oh, easy now. 1, 2 are the first 2 rows we don't need, and then we always have 3 columns. What do I need? And then I have 5, so 1, 2, 3, 4, 5. So the first ones I don't need these. 0, 1. The last column is minus, plus, minus, plus, minus, plus, minus. You just alternate all the way down. This will have the 581 on it. This will have the 427 on it. This will be the coefficient. And then what do? I write them backwards, not 1, 2, 1, 3, 2. I have to write them as 2, 3, 1, 2, 1 are the coefficients. Now what am I doing? 2 times 1 plus 0 is equal to 2. 3 times 2 plus 1 is equal to 7. 1 times 7 plus 2 is 9. 2 times 9 plus 7 is equal to 18. 25. 1 times 25 plus 9 is equal to 34. Therefore, if we did this correctly, this says that 7, which is the GCD of 581 and 427, is equal to 25 groups of 581 plus negative 34 groups of 427. If you check, it does work. I made sure before I did the examples. But this is how you use the Euclidean-Bezoutian algorithm to find the GCD of 2 numbers and then write that GCD as a linear combination of the original 2 numbers. Please subscribe right here. Hit the notification bell. I'll see you next time.